All right, we're going to be moving on. Our next presenter is Deacon, G4IFX. He's going to be talking about consolidated amateur radio reports as indicators of intense sporadic E layers. He is virtual, so if you'd like to share his screen.
Okay, so can you see that? Oh yeah, I can see it on the screen behind you actually. Great. So hello everybody. I'm sitting somewhat to the south of London, where we're having a very nice early spring day. It's very unusual for the weather in England to be better than the weather is in Huntsville. I'm quite sure. So I've been a radio amateur since I was 16 years old. But for the last few years, I've been doing a part-time PhD with Catherine Mitchell at the University of Bath, with the subject being Sporadic-E, or at least understanding some aspects of the propagation mode called Sporadic-E. And I just want to get rid of my own picture there. Okay, so last year I spoke about my polarization research, and I'll just give you a quick refresher on that, and also some new slightly new results which you might be interested in. But that's really just to set the context for what my talk is really about, which is yet another way of using crowdsourced amateur radio data to do some interesting science. In my case, it's actually a fairly simple thing. I need to be able to establish for my other work that I'm actually receiving sporadic-E signals rather than something else. But actually, it offers the opportunity to do quite a lot more than that. And if I can make my screen work, here we go. So here's a quick summary on what I did. It was actually in 2018. So looking at the polarization of signals. And initially, I was just interested. You know, I've been on 6 meters for nearly 40 years. I was just interested to know what happens to the polarization, because anecdotally, it can be very elliptical via sporadic-E. So I did some work which then turned into the PhD work, and this is the most recent incarnation of that. So using a crossed Yagi, it's a fairly chunky thing, it's about 30 feet long, up at about 60 feet above the ground, to sample the incoming polarization ellipse, the incoming signal. And if you measure the phase and amplitude difference between the two, the horizontal and the vertical signals, you can in fact derive all the properties, or the important properties, of the polarization ellipse. And I can do that in semi-real time. It's stored information, but then I can play it at real time. The first part of this has first couple of results plus an exhaustive description of the technique been published in IEEE TAP, as you'll see at the bottom right-hand corner last year. So to summarize the results of this, and I realize, I don't know how well the guys of those of you at the back in the auditorium in Huntsville can see this, but hopefully you'll be able to get the general picture. If you look at the map in the middle here, that little red triangle in the middle is my station in the south of England. And over the summer of 2018, I captured signals, polarization data, about 6 different beacons around Europe. Some of them along the orientation, the direction, the route between me and them was roughly longitudinal to the Earth's magnetic field, and some of them roughly transverse, and a few in between. And although I did talk about this last year, what I didn't have was this sort of statistical evaluation of the results across the piece. And what I'm trying to establish here is the polarization still linear, or is it actually elliptical? Question 1. And question 2, on that basis, is there a magneto-ionic component in the way that sporadic-E works in terms of reflecting signals, rather than just being a mirror or being just scattering? So just to explain the top left-hand one a little, just so you can see, we've got 2 histograms here. First is the axial ratio of the ellipse. That's the shape of the ellipse. If you look at the top right here, it's the long axis over the short axis, basically, is the axial ratio. The red line in the middle is 1, and that means circular. Left of the red line means it's left-hand elliptical. Right of the red line means it's right-hand elliptical in terms of its center of rotation. And a linear wave would have pretty much, well, a pure linear wave would have infinite axial ratio, because of course there is no width to that ellipse. The reality is a little bit more realistic than that, but I guess you'd say that more than 50 or 100, this is a log scale along the bottom, by the way. So there's 1 there, 10, 100, and 1,000. So anything over 100 or probably a bit less, you'd really, to all intents and purposes, would be linear polarization. The other histogram is the tilt angle, this angle here. So what happens, all the beacons I looked at were transmitting linear polarization, most of them vertical, this one actually horizontal, but it was mainly coming in at an angle of about 45 degrees to the horizontal. So just to go back then, you don't need to be able to see the detail to see that all of these beacons, the majority of the axial ratio data, the left-hand histogram in each case, and those are the proportions of the samples which were in that sort of range, they're all close to the red line. The left-hand charts are all close to the red line. The polarization of a sporadic-E signal is varying the whole time. And not surprisingly, it rotates. And it does actually go through linear and out the other side. But you'll see that very little of the time was spent with anything like 50 or 100, an axial ratio of 50 or 100, bearing in mind that linear polarization and circular polarization are special cases of elliptical polarization. So that's a quick, this is basically publishable, but I need to do something to add to it to justify the results. So how can I show that these signals were actually received by a sporadic-E? Now, I've been on the band an awfully long time. Any of you who are 6-meter operators would be able to say, yeah, I know when it's sporadic-E or not, but that's not enough, obviously. There are other mechanisms. I think F2 was pretty unlikely and close to solar minimum in 2018, even on 10 meters, let alone 6 meters. But you've got moderately persistent signals. The clouds are not very big, or at least the bits of the sporadic-E which are dense enough to reflect at VHF are not very big, and they move. So how can I demonstrate that sporadic-E was present in the right place and at the right time? Now, the main technique, there was a time back in the 50s and 60s when actually amateur radio data was used to study sporadic-E quite extensively, particularly in the 50s. But clearly new techniques have come along. And these days, if you look at the chart on the left here, you've got things like rocket studies, you've got ISR, incoherent scatter radar, you've got radio occultation of navigational satellites, and of course, ionosondes. But the trouble is, if the bottom axis is the time coverage and the left axis is the geographical coverage. I mean, a rocket goes up and it comes back down in one place. ISR, they're very expensive equipment. They don't operate all the time. And there aren't that many of them around the world. Now, in principle, RO, the radio occultation mechanisms, have a global coverage, but at the moment, there just aren't enough satellites. And when we looked at 2018, there just simply wasn't the data coverage on the dates that I was looking for. So that leaves us with ionosondes. But although ionosondes, many of them, and by the way, these are the ones on the map on the right, these are the ones in Western Europe, which I've been using as a calibration feature, they are quite a long way apart. They, when you think that a sporadic-E cloud might be 100 kilometers, but it's usually less. It might be several hundred kilometers, but usually less, especially, as I say, when you're looking at intense sporadic-E, dense enough to reflect at VHF. And you can see the calibration bottom left here is 200 kilometers and 100. They are hundreds of kilometers apart. So there's lots of spaces in between, and it's hard to get data that justifies the existence of Sporadic-E. Now, you might say that amateur data is up at the top right there, or can be, because of course radio amateurs are actively looking for Sporadic-E all the time, in the summer particularly. So they're pretty likely to land upon a Sporadic-E opening. Okay, so here's the way that the data collection or the data I used, and this is coming from, and like some of the other studies that have been published, like the eclipse work and so on, coming from RBN, from PSK Reporter, from the DX Cluster Network, and from WhisperNet. And I've been doing it using an aggregator called dxmaps.com, which is very good. It's got its own mapping capability, in fact, and it aggregates data from all of those sources. It wasn't very good at collecting Whisper data in 2018. So for that reason, I've had to make a direct route into this as well. So I'm selecting the 28, 50 and 70 megahertz reports on the basis that they were much more likely to be Sporadic-E than anything else. I'm also cutting out data where the distance between the two stations was less than 750 kilometers, to get rid of things like ground wave and tropo effects, direct wave, I should say, not ground wave, and not at 50 megs anyway. And I also had a cutoff at 2,500 kilometers because I wanted single hop. I wanted to be able to know where that reflection point was likely to be. So running all that, then plotted the data on, I wanted to be able to plot things a little bit more flexibly. Therefore, I wrote my own. This has been coded up in MATLAB. So on this chart here, the green lines are 10-meter spots. The blue lines are 50 megahertz spots, and the red, solitary red blob and red line in the middle there are 4 meters, in fact. So that's, and what I've drawn on here is the great circle paths and the midpoints, bearing in mind that I have to make an assumption somewhere, and I'm making an assumption that the reflection point is somewhere near the midpoint, although off-axis reflection is obviously possible. And you can see very clearly a sort of a crisscross pattern there, so that you're getting triangulation on where the Sporadic-E is probably sitting. In this particular example, you've got a nice big blob here and a nice big blob up here. You can also see that the 10-meter blobs are a bit more spread out than the 6-meter blobs. And that's not surprising, is it? Because 10 meters can be sustained by a lower level of ionization than 6. This is my preferred way of presenting the information, partly because the tracks are sort of getting away. They sort of obscure what's going on. So this is just the midpoints. But also the limitation of this technique is that these are signals of opportunity. You don't know whether people are actually transmitting or not. So it's a very good test of where there is Sporadic-E, but it doesn't necessarily tell you where there isn't Sporadic-E. Although on this chart, and what these tiny little dots are, I hope you can see these at the back. There are green ones and there are blue ones. These are all the possible paths, the midpoints of all the possible paths between all the stations that I know were active during that time period. And these are 15-minute periods, partly so that I get enough data to see the pattern, but also because it allows me to synchronize it with the ionoson data, which I'll show you in a sec. So ionosons are very good at helping you detect Sporadic-E. Here's one is from Průhonice, which is the ionosonde in Czech Republic. It is actually from the day of my case study, which you're going to see in a bit. Broadly, just simplistically, Sporadic-E is at about 100 kilometers and it's flat. E-layer and F-layer propagation has this, obviously it's at a greater height, but also it has this curve to it because of retardation as the wave gradually bends through the ionosphere and curves back to the Earth. Sporadic-E is very thin, it's very intense, so there is no difference between the actual height and the virtual height, if you can believe that. So there's a very different pattern there. And here's an example of a much more intense phase of the Sporadic-E. It's also from the same afternoon, actually. And I've chosen to use as my sort of calibration marker the top frequency, the highest frequency that's reflected from the Sporadic-E. Vertical incidence, by the way, this is ionosons are vertical echo sounders which sweep the frequency from low to high. Okay, so you're about to see a video of the case study, which is 16 samples across the afternoon of the 18th of August 2018. So there's a base map. There's the spattering of all the possible paths from the stations I know were active in that 15-minute period, because you've no other way of knowing what the coverage of the data is. And there are the midpoints of those paths. The blue ones are 6 meters and the green ones are at 10 meters. And then finally, there's the corresponding ionoson data. Bear in mind, though, of course, the ionoson is actually measuring for a couple of minutes in the middle of this time period. So to expect complete and total alignment between the two, bearing in mind how small some of these Sporadic-E patches are, is rather hopeful. But my goal here is to establish the plausibility of using the amateur data. And you can very clearly see here, by the way, in the gap between these two, that there was actually pretty good coverage of in terms of amateur stations which were transmitting on those two bands, 10 and 6, and active at that period. So probably there is a trough in the Sporadic-E along that middle line there. Okay, so here we go with the video. I'll run it through, and I think you can see the sort of development that happens to the opening, and you can also see that there's a broad correspondence, although it's not absolutely totally 100%. And this is at the end of the period. This is 5 o'clock, 1700 UTC, and you can see that actually the Sporadic-E has disappeared. In that means no measurement, no Sporadic-E detected by the ionosons over here to the east, and there is in fact a band of Sporadic-E left. It's mainly only reflecting 28 megs rather than 6 meters, because it's not 10/10 enough. But you know, again, so you can see the sort of development of it. So it meets my needs in terms of saying, yes, there was Sporadic-E that day, but also it offers the possibility of doing more interesting things to plot the evolution of events. This is all the mapping and everything, by the way, is written in MATLAB if anybody wants to have copies of it to do their own analysis. There's a bit of manual labor involved, but all the map plotting is automatic. So there we are, the conclusions. I do believe this is a valuable indicator of the presence and development of Sporadic-E. I think it's the first time that in the modern era that this automatically collected data has been used to study Sporadic-E. And if there isn't any coverage at the right time in the right place, e.g. from the radio occultation satellites, then the amateur data might be the only independent evidence that Sporadic-E was present. But bear in mind, amateurs spend their time, because I'm one of them, you spend their time looking for Sporadic-E every summer. So the chance of actually finding an event are pretty damn high. But obviously there are some limitations. Signals of opportunity, they go on and off. It's not so good at demonstrating where there wasn't Sporadic-E. And obviously this is only really going to work unless you're looking at one path and you happen to have somebody sitting in the right place where there's a relatively high amateur population. So Europe, Western Europe, certainly North America, Japan would be good places to be doing this thing. So there you are. That's what I've been talking about. It's yet another use for amateur crowdsourced data, exploiting the fact that we have lots of people in lots of places. And any questions?